Okay, today we're going to work on a review. So the first question says, the above graph was made from data collected during an investigation of the relationship between the amount of two different springs stretched when the force is applied. For each spring, determine the spring constant. F equals 20, A equals 0.5, B equals... So basically it's saying on this graph, it doesn't give you numbers in advance, but here are the numbers right here, 20, 0.5, 1.1. So spring constant, since we have force and we have distance, our spring constant, we're going to use the F equals kx equation. So 20 equals k times 0.5. So divide both sides by 0.5. And we get for this first one that k is 40. And then we have F equals kx, so 20 equals k times 1.1. So divide both sides by 1.1. And we get that this k is 18.18. Okay. 40, 18.18. Newtons per meter are the units of the spring constant. How much work is required to stretch spring A from 0 to 1.05 meters? Okay, so work is the change in energy, right? Which is energy final minus energy initial. And energy initial, in this case, is 0. So she's starting from 0 meters. There's no work required. There's no energy in the spring at 0 meters. So we're just looking for the final energy. Final energy is spring energy, so we're just looking for ES equals 1/2 kx squared. So 1/2 times 40 times 1.05 squared. Okay. 0.5 times 40 times 1.05 squared. And we get 22.05 joules. Okay. Suppose W is the amount of work done stretching a certain spring from 0 to 20. How much work is done to stretch the same spring from 20 to 40? Draw a graph and compare the area. Remember, the idea is that if we have a spring graph that look like this, where the force and the distance. Now, to go to 20 centimeters, it requires, this amount of force. And to go from 20 to 40, notice there's more force required. It's not the same amount of force anymore. The area under this shape is actually going to be 3 times the area under the first shape. Okay, if you wanted to, you could go back and solve for k in terms of x and everything, but looking at the graph, you can just know. To go from 20 to 40, it's going to be 3 times as much energy. Or to go from 0 to 40 would be 4 times as much energy, because it requires more energy to pull a string that's already been stretched than to pull a string that hasn't been stretched. Okay, so a 6.9 kilogram brick is falling at a rate of this towards the earth at a current height. Total energy. So what kind of energy am I dealing with here? I've got, first of all, it's high, right? So I've got some EG, and it's moving fast, so I've got some EK. The brick is not compressed or stretched or anything, so I don't have any spring energy. So I've got mgh plus 1/2 mv squared. So m is 6.9 times 10 times h is 7 plus 0.5 times 6.9 times 28.8 squared. So we have a total of 3,344.56 joules of energy. Okay? I guess I could write that out. 6.9 times 10 times 7 plus 0.5 times 6.9 times 128.8 squared. Okay. 500 kilogram go-kart is traveling at 11 meters per second when the driver slams on the brakes. The cart comes to a stop in 10 meters. If the same braking force is applied, how far will the cart travel after braking if it were traveling 47? Okay, this is a little bit more complicated. first thing we have to figure out is change in energy. Okay, so the beginning of the story, you've got kinetic energy. EK is 1/2 mv squared. So you've got 1/2 times 500 times 11 squared. Okay, 0.5 times 500 times 11 squared. So you're going to start out with 30,250 joules of energy. Now, you slam on your brakes, you come to a stop, you've lost all that energy. In other words, your brakes have done work. So your brakes cause a change in energy. So the work done is that 30,250 joules. But remember, work equals force times distance. So we can take our 30,250 joules, set that equal to force times 10 meters. Okay? So we divide it by 10, and we find that the force the brakes can apply is 3,025 newtons. So now we need to do the problem a different way. We still find the total energy of the cart when it's going 47. So again, it's 1/2 mv squared. So 1/2 times 500 times 47 squared. And so in this case, we get 552,250 joules. And that's going to be all your energy that you're going to lose. So that's going to be your work equals force, which we already decided was 3,000 times distance. So we take our work divided by our force, and that will give us our distance. Or in other words, this number divided by 3,025, and we get a distance of 182 meters. So even though we're only traveling 4 times as fast, it takes us almost 20 times as far to stop. Certain spring is found to stretch 0.09 meters when a force of 5.4 newtons is applied. What's the spring constant? That's going to be F equals Kx. So 5.4 equals K times 0.09. So 5.4 divided by 0.09, and we get the spring constant is 60 newtons per meter. How much work was done by the first one in the spring? Okay, work is change in energy. You have no energy to begin with, so our work is going to be the same as our spring energy, or 1/2 kx squared. So 0.5 times, we said 60, times 0.09 squared, and we get 0.243 joules of energy to move it that much. The block is placed on a spring with a spring constant of that, compressing at that. What height does the block reach when it is launched? Watch your units carefully because we're going to have to change centimeters to meters. So at the beginning of the story, we've got EG. At the end of the story, we've got, at the beginning of the story, we have ES, spring energy. At the end of the story, we've got EG. So we have to do 1/2 kx squared equals mgh, and we're solving for h. So we can divide both sides by mg, and so we get 0.5 times our spring constant of 107 times our distance of 0.48. This becomes 0.48 meters, okay, squared, divided by our mass, which is 463, divided by gravity, which is 10, and we get our height of 0.002662 meters. So not very high at all. Okay. A box is released from rest on a frictionless ramp. How fast will it be moving at the bottom of the ramp? Okay, so at the beginning of the story, we've got height, or gravitational energy. At the bottom of the story, we have kinetic energy. So we have EG equals EK, so mgh equals 1/2 mv squared. Our masses can cancel out, and so we're going to have GH, which is 10 times 1.25, or in other words, 12.5 equals 1/2 times v squared. So divide both sides by 0.5, and then square root both sides, and we get that velocity at the bottom of the ramp is 5 meters per second. Okay, so now we go to the last problem, and we're going to have a math student hikes a mountain, her altitude increased by that much, find the power, took her 3 hours. Okay, the only energy that's changing here, because remember power is the change in energy over time. The energy that is changing here is gravitational energy. Since you start with none, your change is the same as your total. So then our power here is going to be mass times G times H, all divided by T. So it's going to be 65 times 10 times 1500, all divided by 3 hours. So we have to times it by 60 to get it into minutes, and by 60 again to get it into seconds. So it's 65 times 10 times 1500 divided by 3 and 60 and 60. And so we end up with 90.27 watts. Okay, so lots going on here. Some big equations to remember, obviously, are the F equals kx. You've got the spring energy equation. Energy of a spring is 1/2 kx squared. You've got the gravitational energy, which is mgh, and the kinetic energy, which is 1/2 mv squared. You've got power, which is change in energy over time. Some other equations that aren't on here are power equals force times velocity. You can use that one, and yeah, good luck.